novel search strategies for SETI. Vishal Gajjar is a project scientist with the Breakthrough Listen group at Berkeley, and he works to enable SETI experiments with radio telescopes around the globe. Thank you very much for presenting this seminar, and please get started.
Thank you. Thanks, Daniele. Thanks for inviting us to share our work with your group. That's very exciting. Hope we will be able to convince by the end of the talk that this is something that you feel all excited about. Just share my screen. Are you all able to see it?
Yeah, I can see it.
Okay. All right. Yeah, sorry for the long title, but basically what we want to convey with this talk is that the summary of the Breakthrough Listen program. So over the talk, we will try to give you a flavor of various things that's happening within the group. We have our students who are working with the group who will talk about a specific aspect of the project. Karen will talk about our recent survey, a paper that we recently submitted on the Galactic Center. Bryan will talk about our efforts to search for different types of signal using machine learning tools. So before we begin, this is one of the sort of the classical question for mankind. Are we really alone in the universe? And there has been a lot of work and effort has already been happening in this area. If you ask this question to maybe, are we able to kind of answer this anyway better than a few years ago? I think we are moving in that direction. Because right now, although we don't have JWST kind of telescope, but hopefully in future we will, and those kind of facilities will be able to detect atmosphere of some of these exoplanets that we are discovering almost everywhere. These exoplanets atmospheres will be able to point us if there are any biomarkers which are telltale sign of existence of life on those planets. But pushing this question further, is there a way by which we will be able to do this for a large number of stars? The answer is not with the existing technology. Even with the JWST, you will only be able to do it for only a handful number of stars, not for too many of them. And then the question comes, how do we find intelligent life? Because with this technology, maybe we'll find that there is some kind of a bacterial life or some biological processes which is producing these chemicals, although they will still be debatable because if you look at the literature, all the biomarkers, some of the biomarkers also have natural processes can give rise to those as well. So, I mean, there's always going to be a debate whether the detection that is truly due to a biosignature or due to nature processes. I mean, recently Venus phosphine is a good example of that. So the question is, can we detect evidence of intelligent life? And then that's kind of a typical question to answer because we don't know what are the signs of intelligent life. We try to think from our own side, like what are the ways by which we can detect our own technology, like. And we think that that electromagnetic waves is one of the best possible ways by you can detect Earth. And after the electromagnetic waves from ground-based instrument, we can easily record a large spectrum of the electromagnetic waves, which is the radio band. So we think that the radio waves, again, there are other reasons to choose radio waves for detecting ETI. First, radio waves are far easier to generate. They are much cheaper to generate. They can convey, they can travel up to much further distances without being absorbed. So you can transmit radio signals with a very minimum amount of energy, and you can transmit that to a large distances all the way across the galaxy, be detectable. It's not typically true for other types of such signals. It's much harder to generate, and also it's more expensive, and then it's required much higher energies for doing that. So we think that although there is no restriction, we should really not constrain our search to radio, but given the current technology, we think the radio is the best possible way to detect evidence of intelligent life. So if I ask this question, how are we thinking about this thing? So we take an example of Earth where we had life, and after time we have intelligent life, we produce technology, and this technology ultimately produced radio waves. Now these radio waves produced from any planet out there are traveling. Even if the life on that planet is perished, there is this bubble of emission of radio waves, which is still propagating throughout the galaxy. So anywhere else in the galaxy, if you have such transmitter produced only for a fraction of time in their lifetime, you still have these limited ring of radio emission, which will be propagating throughout the galaxy, even after they stop, if either due to their own sort of exist up there, they get perish, or they stop transmitting radio waves due to some other reasons. But then there is still this ring of emission, which will keep on expanding throughout the galaxy, even beyond our own galaxy, right? So this is the hypothesis, like at any civilization out there in our galaxy, at any point in their lifetime, produce sufficiently strong radio waves, with whether we're able to detect it or not. So when we talk about these kind of radio waves, there are two typical types of radio waves we mentioned. First is the deliberate beacon radiation, the signal which are purposefully transmitted for our own detection. So like you make the signal so bright and so strong, and you make them so unique that they can not be mistaken for being produced by any kind of nature processes. These are what we call beacons. So they are they cannot be produced in nature. Arecibo radar signals, although not being particularly transmitted for that purpose, but can be considered as kind of like beacons. Unfortunately, probably all of you must have seen the news today about Arecibo, so it's unfortunate. But those signals produced by Arecibo radars are so powerful that you could detect them all the way across the galaxy. So those are some of the brightest of the bright signal that we as a human have produced so far. Then there is also what we call the leakage radiation. Like if you have come to the Bay Area, you might have seen the Sutro Tower, right, in San Francisco. I mean, signals from Sutro Tower is pretty strong, but you can only detect it only a few light years. You cannot detect it beyond that because it's very weak. Signals, for example, we use to detect aircraft. So aircraft radar signals are still strong, but they are not strong as like Arecibo radar. But they are leakage radiation. So these kind of signals are not produced for the purpose of they being detected by ETI. They are produced for our own usage. So they are basically a byproduct of technology. So there are two different types of signal, a deliberate beacon signal, which are clearly distinguishable from natural signal, and then the byproduct signals, which could be similar to natural signal, but there are ways by which you can distinguish them. How do we search for them? So this is a very difficult question because we have absolutely no idea about where to start with. So if you talk about the different parameter space in SETI, people talk about total 9 different parameters. So first of all, we don't know where signal is coming from. So you have the 3-dimensional problem, like with direction to point your telescope, how long you need to integrate because it's in the 3 dimension, how far the source is. You also don't know in which part of the sky the source is located. You don't know. The time, because all the signals might not be transmitting at all the time, but at what time is the best to kind of look for them. Whether we have enough sensitivity, I mean, is by building better and bigger antennas and more sensitive antennas, are we really pushing the limit? That sensitivity is, again, one of the parameter space that we should explore. Polarization, we don't know whether signals will be polarized, whether we should be doing a very detailed polarization search, or we should just look at the signal in total intensity. Biggest problem, frequency. We don't know whether signal, even if we consider the electromagnetic radio waves has a lot of frequency coverage. None of the single telescope that we have at the moment can cover the entire radio spectrum. They can only look at a very small part of the radio window. And then you can kind of switch between different receivers to cover the entire radio window as much as possible. But we cannot look at the entire radio window at the same time. So obviously the limitation is we don't know at what frequency the signal is coming. So that's a parameter space. We don't know the modulation scheme, whether the signal will be of any particular type, whether our classical sort of like a approach of detecting a signal will be sufficient to detect these. We don't know if signal will have some particular type of modulation, which we'll not be able to kind of identify, or we'll not be able to distinguish it separately from natural occurring signal, then we might miss it. So with all that in mind, obviously with these challenges, Breakthrough Listen was announced as a part of the Breakthrough Initiative. Breakthrough Initiative is a larger umbrella under which you have lots of other programs. You might have heard about Breakthrough Starshop. You might have heard about other sort of programs which are related to Breakthrough. Breakthrough Prize is also another sort of example. So Breakthrough Listen is a part of the Breakthrough Initiative, launched in 2015 at the Royal Society London. And we have a Breakthrough Listen advisory board, which used to be led by late Stephen Hawking. Now it's currently being led by Professor Martin. And we meet yearly to basically talk about different ways by which we can improve our search, different ways by which we have kind of improved our limits over the years, number of targets that we have searched. To give you an idea about what exactly we are searching for in the Breakthrough program, there are different types of sources that we search within the program. But we can classify them into these 4 different categories. So we have a target list of 1 million nearby stars. So we are searching for almost 1 million stars, which are closest to us. For signals which are produced by sort of technologies, which is you can consider as a kind of like a leakage radiation. So we are more sensitive to this 1 million nearby star. But we don't want to limit ourselves to search only this star. We want to extend it beyond. So we are also searching for most of the nearby galaxies. So signals which might have been produced by more advanced civilizations. So there is a scale in ET and in sort of a SETI literature, which we call the Kardashev civilizations. So as civilization gets more and more advanced, their energy needs will keep on increasing. And at some point, they will be at a level that they need to kind of occupy they need to harness the energy of their parent star. This is what we call K2 civilization. And then beyond that, you have the civilizations which are so advanced that their energy need can only be satisfied by harnessing the energy of the entire galaxy. These we call the K2 and K3 civilization. And these are like super highly advanced civilizations, millions of years ahead of us in technology. Do they exist in our local universe? To answer that question, we are searching for all of the nearby galaxies. So even if these galaxies are far away, but if there are at least a few number of such intelligent civilization out there, we will be able to detect those within these galaxies. We are also kind of not constraining ourselves to just look at the stars. We are doing a blind survey as well, a blind survey of the entire galactic plane as well as the galactic center. And Karen will talk more about the galactic center campaign with the Breakthrough Listen program. We are also exploring exotic objects which defy our current understanding of physics, things which are anomalies, things which are extreme in their behavior, which are harder to explain by our current physics. We are not saying they are due to ET, but they are still worth a look. So we are not excluding them from our analysis. So we are not just targeting stars, but we are also looking at these objects which are outside of our current understanding. So in order to cover all that, these many targets, there has not been such effort has ever happened in the history of SETI in this field. This is the first time where we, as a sort of have taken this step to actually explore and take this question to a new level that has not happened in the past. So we typically say that 1 day of Breakthrough Listen is typically like a 1 year worth of previous SETI searches, because earlier SETI searches were targeted only a fraction of the frequency band, and they were only searching for a very few stars. So by extending the number of targets, extending the parameter space, we say that the amount of data we collect in 1 day is equal to the amount of data typical previous SETI surveys would have done. And the best thing about this is that all of the data we collect is accessible to public. So if you go to the Breakthrough Initiative Open Data portal, you will be able to download all the data that we have made public from most of our observations we have taken so far. So how do we collect the data towards these targets? So for that, I'm only talking about the radio. I'll talk about the other facilities. These are 2 of our primary radio facilities, the GBT and PARCS. GBT, because it's the most sensitive instrument. It's a most single dish telescope. It has a large frequency coverage going from 300 megahertz to all the way up to 100 gigahertz. It has a very flexible design. So we have an instrument which can simultaneously tap 10 gigahertz of bandwidth from the telescope into baseband row voltages into our backend. So we have a very flexible and very versatile backend at the site, which are also being used for other science purposes. For example, searching for FRBs, looking at FRBs at much higher frequencies and other purposes. We have 20% of the time being dedicated at GBT just for doing SETI from GBT. Similarly, for the southern part of the sky, we use the Parkes telescope. Parkes is also one of the most sensitive instruments in southern part of the sky. At this moment, they have a new upgrade of the ultra wideband receiver, which goes from 0.7 to 4 gigahertz. So it gives us a good frequency coverage, and we are going after many targets. We already completed the galactic plane survey. So the one thing I mentioned earlier about the galactic plane and the galactic center thing, we completed the galactic plane survey twice from the Parkes telescope using the multi-beam receiver. And we are now moving towards other targets using the UWL receiver. One of the telescopes that we are most excited about is the Meerkat telescope, which is coming online. But at Meerkat telescope, we don't have a dedicated time. We are going to operate more in a commensal mode observation. So for example, if there are other observations, for example, if a primary observer is looking at a pulsar, and in the same 1 square degree field of view, if there are interesting targets, which are important for SETI, we will form our own beams within the primary beam. So we plan to form something around 64 beams inside the primary beam and do a commensal observation. And this is what I was kind of discussing it before we started the talk, is that we will form 64 beams and we process all of them in real time. And to do that, we have 128 node compute cluster, which we have currently in the process of deploying at the Meerkat site, which will allow us to do this thing in real time, which is going to be a huge challenge. But the technology exists, and we have it already in our hand to basically push this limit as something that has not been done before in this area. Just to give a brief outline of all of the other facilities that we collaborate with as a part of my job, I collaborate with a number of other observing facilities where we either go as a sort of in a proposal-based mode, which we apply for time or collaborate with these facilities. We build instrument and we deploy them over there to do the science type of science we want to do. So there are more than half a dozen facilities which we collaborate and work to do SETI. And obviously this is something unique. Something like this has not happened in this field. So again, we are exploring a different parameter space with the highest sensitivity possible, with the best instrument that's available to us from all of these sites. Just to mention, there are also not just radio facility, we also have a couple of optical facilities like the Automated Planet Finder and Veritas, which does the optical SETI. But in this talk, we'll not have time to go much deeper into those. So what are the type of signal we typically search? So we try to search for various different types of signal, obviously. I just give you an example of two of them. One which we call the narrowband signal. So all the natural signals are very broad in frequencies, but the artificial signal that we produce by our technology are pretty narrow. So almost all of if you look at the literature, almost all the previous SETI searches have been done. They all look for narrowband signals. So that's something we should definitely be doing. And we are already doing that. Karen will talk more about the challenges of finding these narrowband signals and how we try to kind of come over. The other type of signal are the broadband dispersed signals or broadband dispersed pulses. So you're all familiar with typical dispersion curve. We know that nature produces these signals. Now we ask this question, nature doesn't produce something like this. This is what we call artificial dispersion or negative dispersion. Now this has been proposed in the literature, but nobody has really searched for this signal, which actually drifts in a negative direction, which nature doesn't do, at least what we have seen it. Can we search for them? So this is the hypothesis, obviously. We don't know whether ETIs are doing it, but the argument is that if ETIs already know about FRBs and pulsar, they know about the natural dispersion, they will try to mimic these signals with the added artificiality for us to distinguish them separately from natural occurring signal. And that's why we think that signals like these would be a good way to search for artificial beacons. So what I'm showing you on the left, that's a positive DM or classical dispersed pulse that you will see from pulsars and FRBs. But then there are also other 3 different kinds of artificial DM signal, which we don't typically search for. And they could still be served as a beacon. We don't know, the hypothesis, so we are testing it. So for that, we have built a pipeline called SpunDuck. So spandak I mean, I'm from India, so in Hindi, it means pulsating object. So anything which sort of gives pulses. We use Heimdall, but we basically use various different ML algorithm to classify these signals and eliminate as many false positives as possible. I don't have time to go into the details, but we use this pipeline to search for dispersed signal quite often. In fact, we have used it to detect the fast radio burst, the first repeating FRB at the highest radio frequencies. There are other classes of signals. This is the third category of signal, which we call the modulation signal, right? Signals which have some kind of an embedded modulation in them. We know something around 24 different types of modulations that we have basically come up with. We are already designing machine learning algorithms to search for this different kind of modulation signals. So I will take, I think if we have any questions, I probably will kind of skip towards the end and then I'll be happy to answer those. So now let's switch to Karen. Karen, do you want to share your slide?
Yeah, hi. So now I'll talk about one of the main targets of Breakthrough Listen, which is to survey the galactic center across the widest radio frequency range ever covered, like Vishal already mentioned, to look for signs of intelligent life by searching for narrowband signals alongside the broadband signals that Vishal just mentioned as well. So why are we looking at the galactic center? Well, the line of sight towards the galactic center has the largest number of stars in any given direction of the sky. It's also a potential location for an intentional beacon built by an advanced intelligence. And it's the most energetic region in the Milky Way. So taking this first point of the galactic center having the largest concentration and highest number density of stars within our Milky Way, these stars have had a larger time to develop habitable planets due to the inside-out formation of our galaxy. And because of this, these planets have also had a longer time to develop intelligent life, as you can see in this figure on the left, where it's estimated that near the galactic center, as many as about 10% of stars can have at least one habitable planet. The second point uses the Schelling point idea from game theory, where the point is defined as a solution that two sets of people, or in this case, civilizations, choose by default when they cannot communicate. So like an example of this is if you're in New York City and there's no way for you to communicate with like a friend that you're trying to meet up, where would you meet and at what time? And the most likely scenario is that you would probably meet at noon at Grand Central Station. Similarly, we can apply the Schelling point to search for intelligent life, where we have this large amount of space that we can't cover. So we have to narrow down our search. And we look towards the galactic center for the reasons mentioned earlier regarding it being the most likely region to host intelligent life, but also the fact that the galactic center is the center of the entire galaxy. So it's the likeliest region for a civilization to put a beacon on or near it, since it would maximize the detection across the entire sky. So past surveys like Shostak and Tartar have conducted searches looking for narrowband signals, but they only cover a very narrow bandwidth range, like looking specifically at the 21 centimeter hydrogen transition line around the 1.4 gigahertz frequency. So this survey will be the first to cover a wide range of bandwidth at a high sensitivity, producing high resolution data products. We'll be using both the Parkes telescope in Australia and the Green Bank telescope in West Virginia to expand this range, where we will be observing from 700 megahertz to 93 gigahertz with a total combined observing hours of about 600. And our observing plan includes using the ultra wideband receiver at Parkes to cover the lower end of our frequency range, 700 megahertz to 4 gigahertz, as well as using the 7 different bands in Green Bank telescope to cover the rest of our frequency range. So for each band, we will do both deep observations of the galactic center bulge, as well as shorter 5 or 10 on-off minute pointings around the bulge. So the longer observations are going to be used to look for both physical and artificial broadband signals, and the shorter observations are going to be used to look for narrowband signals. So far, we've completed the C-band of Green Bank telescope between 4 and 8 gigahertz, and we only need about 2 more hours of deep observations, but we've completed all the short observations to look for narrowband signals. And we've also conducted the first 14 short pointings of Parkes telescope, which I'll show these later on. So to search for narrowband signals in our data, we use TurboSETI, which is a breakthrough listen code designed to look for narrowband Doppler drifting beacon signals, where a beacon is a continuous sine wave transmitter, and we channelize to 1 Hertz to optimize for these signals. So I'll go over this histogram in a bit, but if you look at this TurboSETI pipeline, if you just look at the green section right now, I'll come to the rest later on. We specify search parameters such as signal to noise ratio and drift rate. Because searching through the entire parameter space is computationally expensive, we only choose like an SNR of 20 here and a drift rate of plus or minus 4 Hertz per second. So if we go back to the histogram, you can see all the hits found as a function of frequency for both of our telescopes, the Green Bank telescope and the Parkes telescope, for our 18 hours of observing so far. And keep in mind that these are total numbers of hits across all of our observations. So now we have to identify signals from these hits, right? So you have all these hits. How do you identify any signal? So we apply this on and off method to identify interesting signals from radio frequency interference, or RFI. So by choosing an off pointing for each on source and alternating between the two 3 times for a total of 6 observations, 3 for the on and 3 for the off, as you can see here, you can identify any possible signals in the data. So this method helps us get rid of any RFI from Earth-based sources, because it would any RFI would appear in all 6 observations, whereas a true signal would only appear in the on scans and none of the off scans. So in addition, signals due to RFI would appear as having a no Doppler drift, because it would be originating from terrestrial sources. So they would appear as a straight vertical line. But a true signal from outer space, whether it be a satellite or something else, would have some Doppler drift due to the relative acceleration, relative difference in velocity between the transmitter and the receiver. So an ideal potential ET narrowband signal would appear in all the on scans, as you can see here, and it would be non-zero drifting. So we'll look at some of these examples later on. So here we have our observing plan for the C-band of the Green Bank telescope, where you can see an example of the 5-minute short on-off pointings, where the galactic center is labeled as A00 in the middle. And we have a set of 3 instead of 2, so we'd have 9 observations total, 3 for each pointing. And you can see here that we make sure that the on and the off pairs are kept 1 beam away, to avoid any double detection of possible potential signals. Similarly, for the Parkes telescope, you can see the galactic center bulge center in the middle of the diagram labeled A1, and the dotted line here is denotes like the half power beam width, which is 30 arc minutes. So here the pointings labeled A1 through A7 are the on sources, and the ones labeled B1 to B7 are the off sources. So again, we want to make sure that we stay 1 beam away, and here that's like 30 arc minutes to avoid any double detection, just like for the Green Bank telescope. So now we can go back to our TurboSETI code and look at the other half. But first, I just want to remind you of the roughly 2 million hits that we detected across all of our short 5-minute observations. So here's the histogram again. And now that I've gone over how to compare on-off observations, we do the on-off comparison to find events which are non-zero drifting and meet either our filter 2 or filter 3 requirements. So filter 2, as you can see here, defines candidates seen in at least 1 on observation, and filter 3 defines candidates seen in at least in all 3 observations, but none of the off. So from the candidates that pass both of these filters, we plot them and we further vet them through visual inspection. And before showing interesting candidates found, I want to show the following histograms. So here you see how the completed histogram of candidates as a function of frequency. So you can see the filter 2 candidates in orange for Parkes and filter 2 candidates in blue for the Green Bank telescope. And then filter 3 candidates you can see in red and black, which is barely visible. And the green circle here identifies an interesting candidate that I'll show in a bit. But for now, it's interesting to see that it is the only candidate within that region of frequencies. So there's nothing else detected around it. This next histogram shows the number of candidates as a function of drift rate. So as mentioned earlier, although hits with drift rates of 0 were removed, a lot of candidates with drift rates close to 0 still go through, as you can see here. So in the future, we'll make sure to account for that. But not removing those in a way kind of helps us, because here you can see like the final histogram of large distribution of events across drift rate and frequency. And you can see that a lot of the events can be rolled out as RFI across different frequencies due to having drift rates very close to 0. So sometimes this helps us when looking at potential signals. So here are some examples of RFI detected. One is clearly detectable through showing, it's shown in all the on and off pointing, so all 6 observations, as you can see. And the other source of RFI is seen as this triplet pattern. But this drift rate is very close to 0, as you can see, and it sometimes even appears in the off observations. So it's most likely due to a terrestrial communication signal, and that's why we rule it out. Here we have an ideal signal, as we discussed earlier, which is non-zero drifting. You can see it has like -0.6 hertz per second drift rate at the top here. And it also shows in all of the on observations, but none of the off. But it's kind of unfortunate because this frequency of 1.38 gigahertz matches that of the GPS satellite Navstar. So we bet this candidate due to it probably being due to a terrestrial origin, but it's a good depiction of what we expect a potential ETI signal to look like. These last 2 candidates are the most interesting probably from all of our data because they're both experiencing high drift rates, but they're not found in all the on observations. So the frequency region for the signal shown in the left, if you go back and look at the histogram frequency for this region, it actually shows a lot of hits. So it can easily be rejected as RFI. And that's why plotting like these histograms is really helpful. The candidate on the right, however, is at 6.4 gigahertz is pretty unique, and it's only seen in our entire set of observations once. So that's the one that I circled in green earlier. But since it didn't repeat during the other on observations, we still discard it as RFI. So yeah, we didn't find any strong evidence of narrowband signals used using our search criteria. But I did want to say that in total, I went through about probably like 50,000 plots, like just visually betting them out and keeping the most interesting ones. And this is only for 16 hours of data across a search parameter space that hasn't been maximized yet. So we have massive amounts of data, and like searching for technosignatures in this part of the project was pretty easy, but in the future, so we attempt to search through larger amounts of data and expand our search parameters. And like I said, this project is over like 600 hours of observing time. And also as we try to continue eliminating more RFI, especially with the constant additions of new satellites put out by certain companies, we will depend on machine learning approaches to help us make these feeds less computationally expensive, which Bryan will now talk about.
Okay, can you see my screen?
I can see it.
Okay, sweet. Okay, great. Thanks, Karen. So now I'll be talking about some of the machine learning methods, and I wanted to just give a kind of overview of some of the more interesting directions we've taken. So I'll touch on a few different projects instead of going into any single one in incredible depth. But to open up, I wanted to kind of motivate why we want to use ML by asking how can we build on the existing searches that Vishal and Karen have already talked about. So first off, TurboSeti, because it excels when it's searching for linearly drifted signals, basically doing an integration-based approach. There are some limitations which you might expect. One is that it'll struggle in RFI-rich bands. If there's lots of signals crowded in the same frequency space, it's going to have a hard time trying to pick them apart, especially trying to find drifted sloped signals. So here's it's a synthetic example, but a case nonetheless where as kind of humans looking at a spectrogram, we can clearly see there's a drifted signal in there. But TurboSeti would have a very hard time picking it out with a high signal to noise. And another kind of aspect of TurboSeti is, as Karen kind of pointed out, you have to set reasonable bounds on it. Otherwise, your computational time can really explode. And one of those is how low you go in SNR, and another one is what range of drift rates you search. So those are both things that can really add up quickly. Another complication, and this is kind of the rest of kind of our search as a whole, is that while TurboSeti excels at linear signals, not every signal is linear. So here's an example from Sheik et al. Of an on-off cadence, where the dashed red line is actually the TurboSeti kind of best fit. And you can see it matches kind of a section of it, but that doesn't follow the overall underlying signal at all because there's this wavy pattern to it. So the question is, how can we handle these at all? It seems pretty difficult with kind of vanilla like integration-based methods. And also maybe there's a way to search for these directly. Maybe there's some interesting signals we actually want to try to pick out and find. So for all of these circumstances, we can turn to machine learning as a really interesting method. Somewhat recently, there have been major advances in ML, and specifically our focus here is on image analysis. The kind of data that we look at, because we can express it as a spectrogram with time and frequency on the axes, they're pretty much like images. So we can use a lot of the same techniques that have come out of computer vision. So I have an example here of one popular object detection method. And it goes through some of the steps. I won't get into the details, but some of the state of the art is able to identify objects that are occulted. Some are behind each other, partially visible, to actually relatively high precision. And the main, again, in this talk, I'm not going to get into the weeds of this, but a very popular neural network architecture called a convolutional neural network, I'm going to call it a CNN going forward, is pretty much the name of the game. That's something that pretty much you can iterate, and it works with sliding windows over an entire image. So it's something that's very specific to the kind of data that we work with. So I wanted to kind of step back and point out that in order to train neural networks, in order to do machine learning, we want to have labeled data sets. And for SETI especially, this is something that's very difficult to come across. On the one hand, depending on your use case and your experiment, we're looking for signals that have literally never been found before. So how can we come up with a labeled data set for that? In other cases, maybe we have found something that we found before, but it was like a one-off case, and it's hard to find multiple examples of this. Where for machine learning, generally you need thousands, if not millions, of training cases in order to get a well-performing classifier. So one solution that we can do to address some of this is to turn to simulations. So within our group, we've created a Python module for making some synthetic narrowband signals and injecting directly into observational data or synthetic observational data. So to the right, I just have a couple examples of what this might look like. The top is a linear drift rate, but pulsating in intensity. And on the bottom, we have kind of a messier signal that looks like some of the RFI we've actually found, where the actual frequency is hopping around, kind of almost like a random walk in a way. And with this tool, we've been able to generate large data sets that are labeled because we're controlling exactly what we're injecting, as well as testing search pipelines like TurboSeti and just trying to evaluate the effectiveness in certain kind of diabolical situations and basically making sure that it works as we expect. So one of the applications of this is going to be the first kind of ML case study that I'll discuss today. Which is, again, that TurboSeti struggles when you have multiple signals within a frequency range. So if we turn to synthetic data, we can generate full data sets and then train a CNN to try to look for these signals and identify it. TurboSETI, again, it does well at actually finding exactly where these signals are. Not much more, like it doesn't classify or anything, but that's a very important thing to do, to find all the signals we can and make sure we aren't missing any, because if the chances are SETI signals are going to be quite dim, and compared with a background of kind of human RFI, we want to make sure we're not missing the dimmer ones. So to this end, I generated two main data sets. One was kind of a check to make sure that this ML strategy would kind of be generalizable and useful. So I generated a data set with only one signal with a random drift rate. And the benefit of that is that we can directly compare that to TurboSETI. And then another data set with two signals, one with the random drift rate and one with zero drift rate, which is meant to kind of simulate a bright RFI signal, because most RFI has zero drift rate. So I just have an example of a synthetic frame of data to the right here. And yes, this is kind of simplistic, but it's kind of a first go around and a proof of concept for using ML in the future. And the hope is that we can generalize this to kind of more and more. One note that I want to make, though, is that for this study, we basically focused on images that are 32 by 1024 pixels. And lots of the state-of-the-art machine learning methods have focused on much smaller, like under 200 by 200 pixels, because it is difficult to find meaningful things in such a broad expanse. Whereas the hope, obviously, we have so much frequency kind of range that we need to search through. We can't afford to maybe like cut it up by 200 by 200. It would just take really long. But going from this, some of the main takeaways from this project were that ML predictions were understandably less accurate than an integration-based approach. However, they were much faster, in some cases 20 to 40 times faster compared to our existing method. Now, TurboSETI, we've had people working on GPU accelerating it, which I believe has gone up to maybe 9 to 10 times faster in some cases. But regardless, there is still a market increase if we're using ML to kind of try to do the same things. And then for the two signal data set, predictions were a bit worse. Again, understandable because you have another signal in there competing. However, for SNRs above 10, we would generally expect errors in the prediction to be around tens of pixels, which out of 1024 is actually pretty decent, because these signals, they aren't just 1 pixel in width. They actually have a broad spectrum to it. So it actually isn't as bad as maybe it sounds, right? And just testing this on some real observational data. On the right here, I have an example of a real RFI signal, and used both TurboSETI and one of our best performing ML models to look at it. Where the TurboSETI is dotted, it looks pretty much on the money because it is integrated. We expect it to do very well. But then our machine learning model in the dashed line comes pretty close. It's not perfect. It's not as good, perhaps, but it still is capturing kind of good information. So these are promising signs going forward. A different area I wanted to discuss is relevant to SETI is anomaly detection, where you're just trying to find snippets of data that are different enough from the rest. And the thinking is, we see a lot of RFI usually. We find something that is unique, perhaps that is unique and a candidate for ETI. So there is a CNN-based ML framework called autoencoders. And the basic idea is kind of outlined on the right here. It's a schematic from Google where you're trying to, you have an input that's perhaps not labeled in the kind of typical sense where you have a collection of data, and all we're trying to do is we're trying to compress it first into a lower level representation, and then expand it again and see how close we can get to the original image. The thinking being that an image has so much information that perhaps isn't useful and doesn't capture kind of the essence of what we're trying to do. So we can compress that to fewer degrees of freedom. And because we understand the nature of the data set, be able to expand it and actually come up with something that's close to what we got with. So this approach approach, while potentially it's kind of counterintuitive, it's yielded good results of like handwritten digit data sets, simple things like this. But people have been working on this in the kind of radio and radio regime with the data we've done to try to look for anomalies. Because let's say you pass in a signal and then it comes out. If it reconstructs well, we expect that we've seen it before. If it doesn't, that means that the model hasn't seen many examples of that, if any, which means that it should be flagged as a possible anomaly and followed up on. So it's kind of a complex method, but it really gets at kind of understanding what have we seen. So something that goes one step further, not just comparing back to itself and other other data, other samples that were like it, is comparing it to actual predictions of the future. So in Zhang et al. 2019, he used what's called a generative adversarial network. That's similar to an autoencoder, where we train a machine learning model to try to predict what is literally the next step spectrogram that we're going to see. So on the right here, we have a couple examples where what we would do is we would train a model by splitting one half of an observation, use that as input, and try to predict the next half of the observation. If it did poorly, iterate, get better, and eventually he was actually able to get meaningful results. So kind of the top result, what we're showing here is, I should say on the two images on the left are kind of full observations with a split in the middle, just to show kind of where the delineation would be. And for the prediction, he took the top half, predicted the next step. So for the top image, that would be kind of an example of RFI that's going through both an on and an off observation and pointing, where they're pretty much identical. There's some kind of image artifacts, but they're pretty much identical. But in the second case, the machine learning model predicts a signal to exist in the off, whereas there isn't one in the actual. So by comparing the prediction with the next observation or the next time step, that's another method of kind of something that's deviating from our expectation, from the norm, that should be flagged as an anomaly and followed up on. So the last thing I wanted to discuss, the last kind of topic is trying to look, instead of trying to kind of search for anomalies or just identifying signals, what if we're trying to look for signals that we think we have some understanding of? So that while this isn't SETI per se, it is very, very in tune with what we're trying to do. So Zhang et al. 2018, what he did was look for FRBs by simulating FRB pulses and injecting them into sample observations, very similar to what we did recently with narrowband signals. Create a data set here, train a CNN model to look directly for things that look like this. And using this method, he was actually able to find 72 new pulses from the repeater 121102 in an existing data set. A lot that were kind of easy to miss with vanilla kind of standard de-dispersion techniques. So this is a really promising thing because it enables us to pursue kind of more creative ideas. So the last thing I want to discuss is a potential idea we're currently working on. It's ongoing research where we want to do a similar approach where, and this ties back to the Galactic Center survey that Karen talked about, where what if we have a narrowband signal that we think is originating near the Galactic Center or past the plane or something like that. We know it has to pass through all the ISM materials. We know that there are effects like scintillation, pulse broadening that we readily observe in pulsars. How can we apply that and investigate that result? And can we basically simulate that, train a machine learning model to look for these signals, and eventually try to find a signal that we've never actually ever observed before? So with that note, I'm going to say thank you. And we'll leave it to any questions or go back to Vishal.
Thanks, Brian and Karen. That was great. I think we'll take the questions at the end. So let me just wrap it up with like maybe 1 or 2 slides to just summarize everything. So this is going back to the question that Matt asked earlier, like what is the sensitivity, or like what can we place a limit based on various different searches that we are currently doing. So Karen talked about typical searching for narrowband signal using the standard match filtering technique. Brian talked about using some of the ML tools to search for things which are much harder to find. But even with sort of all of these techniques, how much we are able to constrain the existence of ETI transmitter. And for that, we use this parameter called transmitter rate. And you can think of it as the number of transmitter per star. So the y-axis here is in log scale. So if you expect a 1 star out of a million star to have a transmitter, you would find the signal somewhere in the -6 region, somewhere down there. And the x-axis is obviously the total output power of such a transmitter. And what we have done here is basically place all of the previous SETI surveys that has been done and what are the different limits that they place. The 2 lines that you see, the solid line is the total EIRP output of the Arecibo planetary radar. So this is what Matt was asking. Have we done surveys which were sensitive enough to do that? And the answer is yes, so far. The dotted line is the EIRP output of much higher powerful transmitter of what we call K1 civilization, Cardassian type 1, in which a civilization gets so advanced that it is actually able to harness all the energy that's kind of imparts on the surface of the Earth from its parent star. So like if you connect all of this energy and if you're able to utilize all that, that's of the order of 10 to the power 17 volts or something. So you can see that comparing all of the different surveys, these are the limits that we were able to place. And the ideal place we would like to go is this. Obviously, none of the SETI talks is complete without our beloved SETI, beloved ET. That's the place we want to go. We want to do a survey where we have done more number of targets with the best sensitivity. So we think that SETI or the ETI is located somewhere in that region because we have already sort of constrained the region at least above that the plane. With the current Galactic Center survey that Karen talked about, we were able to push the limit slightly lower, but it's still not enough. So hopefully in future, when, for example, SKA will come online, we will be able to go even much further down. Typically, like the leakage radiation that I mentioned earlier, they are not even in this scale. They are at the order of 10 to the power 9 or 10 to the power 8 volts. So it's outside the scale that's been plotted in this figure. So ideally speaking, we would like to go there. So we would like to do million star with that sensitivity, and that would really put a tight constraint on existence of ETI within our neighborhood. But you can still ask this question, like how much parameter space that we have covered. So this is again taking all of the previous SETI surveys, and I'm just plotting into 3 different parameters like sensitivity, what fraction of the sky that these surveys have covered, and what are the different frequency coverage. And if you compare that to what we are planning to with Breakthrough Listen, there is a stark contrast you will see. Like the targeted survey of Breakthrough Listen, although it will only cover a fraction of the sky, but it will be enormously sensitive than any previous survey. And it will cover a large frequency range that has never been searched before. So for example, that Karen talked about, like Galactic Center survey, which goes all the way up to 100 gigahertz. So nobody has done SETI up to those higher frequencies. We also are planning, as I mentioned, the Galactic plane survey, which covers not the entire radio frequency, because currently we don't have technology to do that, but at least a sizable portion of the radio window we would like to cover, at least for the entire sky. Even with that, I think we are still just starting, right? I mean, even if you complete a million survey, that is still a very small fraction of the entire galaxy. So even with this, we will only be saying anything in a very small part of the galaxy, but there is this whole galaxy to explore. So hopefully in future, we will be able to push even further beyond that. But you can always ask this question, like, if I summarize the entire thing, so Breakthrough Listen is still one of the most comprehensive search for intelligent life in the world. In the next 10 years, we will be able to sort of push the limit and be able to put the tightest most constraint on the prevalence of intelligent life. But you can ask this question, like, are these limits meaningful? Like, whether we will be able to say something meaningful out of this. I mean, I can just always mention this, that, you know, this is typically true for any of the natural phenomena as well. Like, anytime we have designed a survey, anytime we have designed a search strategy, our first surveys were never that sensitive to what we actually expected. For example, this is a plot for like a neutrino flux from sun. So when the first experiment were conducted to detect neutrino flux from sun, they were not sensitive to detect up to this limit. And the referee wrote that any experiment like this is not meaningful because it's like standing on top of the mountain and saying that, no, the moon is not there. But I think that's not correct. I mean, the referee is probably wrong, because I think our ancestor did that experiment, and because of that, we know that the moon is not at the height of the mountain. It's beyond that. So even if our limits are sort of not up to the level that we would like them to be, this actually is still a way by which, as long as these experiments are thorough, we are doing this carefully, and progressively putting more and more stringent limit, even if we get the null result out of it. They are important for making this science move forward in this direction. So I will end the talk with that, and I'm sorry to taking it a bit longer than we hope to have done, and we'll take questions. Thank you.
Well, thank you for the very interesting talk. Thank you, Vishal, Karen, and Brian. I suggest that people that want to ask questions can just raise their hand. In the meantime, I have a question from Adam Dunman. Maybe Adam, you want to unmute yourself and ask the question directly. Otherwise, I will.
Sure. Well, thank you for the talk. It's very interesting. I just back to when Vishal mentioned that you expect to find more, or expect signals in the radio, generally that low frequency is preferred. I was wondering if there was like a lower bound on the range of frequencies that you expect to look to search through.
I think, as far as I can say, the current technology limits us. I mean, obviously, the atmosphere doesn't really allow anything below 10 megahertz. So as far as search goes, we will be able to search all the way up to 10 megahertz. If you want to do even lower frequency searches, we have to go to space, of course. I mean, the atmosphere doesn't really allow it. As far as the theory goes, or I don't think so there is any limitations in that. Obviously, the question comes in terms of the energy budget or the strength of such signal. If you go to extremely low frequencies, there are limitations in that factor. We don't use we use kilohertz for our own purposes, but we don't really go extremely low, a few hertz of that range of frequencies. So I don't know. I think if you ask any radio engineer about the choice of frequencies for transmitting over longer distances, probably preferred range is somewhere in the open radio window, which is in a few gigahertz, which is what is preferred. Yeah, there's also a question of like total amount of sort of how much information you can transmit, right? I mean, if you have extremely low frequency, the amount of information you could transmit will always be limited. So you also want to have high frequencies so that you can modulate it and send lots of bits of information along with that. So there are other arguments of like going slightly higher than extremely low physically possible electromagnetic end.
I don't see other questions, so I will ask one myself. I've always been interested what will happen if you actually get a detection. Do you have like a plan about that?
People talk about what in SETI community is post-detection protocol. So in a way, there are ways by which you want to kind of vet your signal, first of all. So there is this thing called Rio scale. A Rio scale is a measure of the importance or like how significant a signal is. So it checks for various things, like the signal needs to be persistent in the sky. It needs to be detected across multiple observatories. It needs to be detected across multiple days and various different, by checking all that, if you're not able to eliminate it, then it becomes interesting. I don't really think that there is a standard sort of a general plan that is in place, that we have to follow this and this. There is no like a red book which will open it in the case of potential signal discovery. I think just like any other science, we will try to kind of find all the ways by which we could explain this. If we fail to explain it by using all the tools that is available to us, we will just leave it to the audience, leave it to the public. Like we will definitely just write it up and publish it, and then we'll ask the general public to, I mean, basically other experts in this area to give us the explanation if we have missed something, for example. And that would be the right way to do it, rather than sort of having something by which we go to the media and announce it. That wouldn't be a right way to do it. I think the right way would be to kind of do this through the proper channel. Like you want to publish it and you want to go through a proper refereeing process, which will take maybe many months to kind of go through all that.
I am sorry because Karina just informed me that there were raised hands. For some reason, they don't appear on my Zoom. Something was wrong. But please, Sabrina, ask your question.
Thank you all for a great talk. I wanted to ask, I guess this question is more for Bryan, but how the GAN prediction of, I guess, the next time step, how that's useful for detections, or how that will fit in with the whole like machine learning SETI pipeline.
Yeah, so a lot of the things I've kind of outlined are definitely kind of proof of concept. To actually kind of standardize it into the actual pipeline would definitely take some more iterations. But the hope is that something like that, I discussed a little the limitations of Turbo SETI and kind of on-off cadences just as is. But one of those things is that if you do have funky RFI and even additional RFI with more complex like structure to it, the GAN proved pretty good at kind of propagating that out and kind of demonstrating the same pattern in a way that's hard to do otherwise. And in that way, that's a way that you can compare, like, okay, this is actually what I expect, rather than kind of an idealized case of like a few straight lines. Because then if you compare that with what actually happened, then there is a difference. So in an actual pipeline, that would ultimately come down to just flagging those examples, and ultimately everything I think boils down to having to look at it and look at it in multiple ways. As Karen says, it requires some human inspection.
Thanks. I see that Emmanuel has raised hand.
Sure, thanks, Daniela, and thanks to you guys. This was terrific stuff. Just really quick, a question for all of you, but I guess for Karen, because she brought it up in her portion. So with the Galactic Center survey you guys have done, and you probably mentioned these details, and forgive me if I missed them, but given the frequency and time resolution with which you're recording those data, or searching even, is there any desire to coordinate with folks, say in the pulsar community, to try to find pulsars in your data set, for example? Because finding a pulsar in the Galactic Center is sort of a huge effort, and the frequency range you guys are working in is ideal, right? People try to go to higher frequencies to avoid the low frequency effects and so on.
Yeah, so we do collect data products that allow us to look for pulsars. So we do kind of do that. I guess Vishal can speak more about that, but our collaborators at Cornell also are looking at these data products to look for pulsars.
Yes, I mean, just to kind of reiterate what Karen already said, yes, we have already collaboration in place to search for pulsars in all of the breakthrough listen data set. So that's currently been led by Akshay and Jim and Shami at Cornell.
Akshay Suresh, is that right?
Yep.
Awesome. Yeah, that's great. Especially because I think the integration times you guys had were like tens of hours, like 10, 14 hours. That's like that's an ideal setup. So that's awesome. I'm glad to hear that.
Yep. In fact, like the first paper we just submitted, I did like a thorough search of looking for transient kind of signals for magnetars. Like, there are suggestions that the galactic center might have more number of magnetars than typical pulsars, although lifetime of magnetar is shorter than typical pulsars. But it doesn't hurt to kind of search for those. And as you know, radio magnetars are typically known to produce bright single pulses than regular pulses, right? So you do want to search for transient kind of signal from the galactic center just in order to see if there are bright radio magnetars. So the paper we just submitted, we did a thorough search of all the way up to, like, I think around 6,000 DM for looking for such transient magnetars, but we didn't find anything.
Sure. Awesome. That's great. Thank you.
I see that Tracy has a question.
Yeah. Hi. I just have a really short question. Thanks again for a great talk. Like everyone has said, lots of fun. I was just wondering about the SETI-Gen simulations. It occurred to me as I was listening about them that they would be perfect for determining the parameters for generating our own signal from the Earth to let other ETIs know that we're actually around. And I was wondering if you'd learned anything from the very, small simulation that you've done so far, and if there were any plans for that in the future.
That's a very interesting question. Definitely not kind of framed in that way. So there is one kind of technicality to what I've done, and it is definitely relevant for kind of the ML searches we've been looking for, which is that this injection, there's kind of a couple ways to do it. One is because we're looking at spectrograms, and for a lot of our cases, we just want to find like whatever is obviously there, because there's a lot that's obviously there that is already difficult to find using just the standard methods. So in order to do that, we can simply overlay kind of a signal onto that like kind of already generated spectrogram and kind of say that's a simulation. That's relatively easy to do. I think the tougher thing is to add it to the raw voltage data that we collect from the telescope and then pipe it through the pipeline to make a simulated observation. While it's not impossible, I think that's a lot better for kind of the dimmest signals, which if it is something that we can generate, it's probably pretty dim. So I think to treat the statistics correctly, we'd want to go that route, which is something we're investigating. But for a lot of the machine learning and a lot of the kind of signal cases, that's just not necessary. So far, it hasn't kind of gotten there. But yeah, that's a very interesting kind of thing to think about for sure.
Okay, thanks.
Yeah, thank you. Thanks once again for the fantastic talk. And I think we need to close it here because we are still in time to the student meeting. Once again, I invite all the students to join the meeting with the speakers. And thank you again, and see you next time.